supervised learning, regression use cases, simple linear regression, multiple linear regression, decision tree, and Python implementations. Okay. So what is regression or why it is used for? So regression analysis, it is now, let's take a step back from there. When we talk about supervised learning problems, we saw last week that supervised learning problems, they have a target variable. That means use cases can be, if I want to, let's say, predict the rainfall, okay? If I want to rainfall of a city based on climatic parameters of wind, temperature, humidity percentage, all of that, I want to predict the temperature or the rainfall based on the historical data of the last 5 years. Now take it to the business world. If I want to predict that how much demand I can expect this year, how much customers I can expect this year based on my historical patterns. Now when I say historical patterns, what do I mean by that? I mean that any business would have some sort of data, historical data. They would, let's say, if I talk about any retail business, right? So they would have items or categories, right? They would have, let me open the Excel sheet. Yeah, they would have customers, they would have stores, they would have items, then they would have, let's say, the sales or the revenue, which I want to predict. So this can be present, this can be there, for the last days, weeks, months, and across many geographies. Now, I have these independent variables to predict this target variable, revenue, right? This is when this target variable is a continuous variable. That means it is a numeric value, it is a continuous variable. Then it falls into the purview of regression problems, right? If this target variable is categorical, that means yes, no, good, bad, right? Fraud, genuine, or let's say multi-class one, where you have red, yellow, green, or let's say a survey is there where you have good, average, bad. In that case, all these are in the purview of classification problems. We will study classification problems in the next session next week, right? Today's session is more focused on the regression problems. That means if you want to predict the value of a continuous variable, I want to predict what is my sales going to be, what is my number of customers going to be, what is the rainfall going to be, what is the parts manufactured in a manufacturing plant. If I want to predict those aspects, then I talk about the regression problems. Yeah. So in regression problems, you have your linear regression is one of the most common and the most frequently quoted algorithm. So linear regression, what it means is that you want to identify the relationship between dependent and independent variables. Dependent variable again is the variable, this target variable, revenue, that is your independent variable, your dependent variable, right? And all of them are independent variables. Okay, so it wants to understand the relationship between them. So what it means is that I want to study, hold on, yeah, I want to study the relationship. What do I mean by studying the relationship? So what can happen is if you think about in a space, in a vector space, so your data sets can be represented, let's say, like this, simple XY coordinate, right? These can be your data points. When I talk about understanding the relationship, I'm saying that based on this data set, if I can create an equation, right? If I can create an equation which best measures the relationship between these variables, that is the purpose of linear regression. Yeah. So simply put, I want to I want to understand this part where my response can be written in the form of an equation, right? Okay. Now, if you see that, what do I want to achieve? Now, this relationship, it can be modeled in many ways. We'll come to that how or what different ways are. But let's say if I have only one variable, only a single variable, then it is called a simple linear regression. And a very simple equation for that, y is equal to mx plus c, that we have studied in our lower classes, that how can you represent a relationship on a line, right? Y is equal to mx plus c. So in that case, x is my independent variable, single variable, and y is a variable I want to predict. That is simple linear regression. And to be honest, you will never ever use simple linear regression in your business world, because in a business world, obviously you would have many more variables. There will never be a situation where you have a single variable to predict. Then that leads towards the multiple linear regression. When I say multiple, it means I do have more than one independent variable. So I have first variable, second variable, and so on and so forth, right? Now what it means, that like this, in this case, you have more than one independent variables. Okay. Now that is, I mentioned linear regression, right? If you extend this concept, to a non-linear regression. When I say linear regression, I mean that y is equal to, let's say, ax1 plus bx2 plus cx3, and so on and so forth, right? That is linear. Why linear? Because the power for each of the variables is 1, right? But you can extend this to y is equal to x square. Why not? Right? You can have equations, you can have your equations where you have y is equal to x square minus, let's say, 3x cube plus 6, giving a very hypothetical equation. If this is the relationship between your dependent, or let's say x1 square, x2 square, right? If this is the relationship between your variables, it is also a regression problem, though non-linear, right? So if you extend this linear regression problem to a non-linear one, you would get something like this. But ultimately, at the end of the day, you want to get this line of best fit, this line of best fit you want to achieve, which is able to define and help you understand the relationship between your variables. That is your objective, always. Okay. Now, then the next question that comes to your mind is that, if that is my objective, how will I measure that is my model doing well or not, right? So these are the ways, for you to understand that is your model doing well or not. Now, in the first one is R square. R square measures that how much randomness in your data is being captured by your variable, by your model, right? So higher the R square, higher is your, or better is your model. But there's a catch in R square. The catch is, if you have, let's say, 500 independent variables, and if you consider all the 500 independent variables, your model will be very complex, right? But your R square will be very high. But that's what you want to achieve. You also want to understand the relationship. That means, out of 500 independent variables, you would want to select which variables are significant, which variables are important for you. So in that case, it is not prudent, it is not a wise decision to select all the 500 variables. You should only shortlist the ones which are important. And that leads to the next KPI, which is adjusted R square. Adjusted R square, or pseudo R square, what it says that is, that if you choose any irrelevant variable in my model, I will penalize you. Okay. So for example, if you have a variable where you have customers shoe number, obviously, and let's say if you sell groceries, right? So customers cell number will not have any customers shoe number will not have any impact on the probability to buy, right? So if you include such a variable in your model, adjusted R square will penalize your R square value. Okay, so in all practical sense, we always prefer to have adjusted R square as the KPI which we want to optimize, which we want to maximize. Okay, then comes to important parameters: mean absolute error and root mean error, root mean square error. So what is the concept behind them? The concept is, if you have this data set, and you created let's say you created, these are your data sets, and you created a line over here, a line of best fit, if you call. Now this line of best fit, for this particular value, your line of best fit, the actual value is this, your predicted value is this, the actual value is this, your predicted value is this, right? So these are the error terms in your prediction, right? Like for this one, the actual value is this, your predicted value is this, very close, right? So what it means is that your error terms, or your model is making some errors, right? Using these KPIs, these parameters, you can identify that how far your model is from the actual predictions. Okay, that is your objective. Ultimately, you would want your errors to be zero. Theoretically, you would want your errors to be zero. It's not possible practically, but you would want your errors to be zero, right? So using the absolute mean error and root mean square error, you can do that. There is one question over here, that why do you do, let's say, root mean square error? So the formula for that is, you calculate your difference, you square that, you take, divide by the number of observations, right? And then you take a root of that. And over here in the mean absolute error, you take the absolute value. Over here, the question comes is that why do we take absolute and why do we take a square? The reason is, let's say if your actual is and predicted, right? Actual is 100, you predicted 101, 102. Actual is 100, you predicted 98, right? Your error is positive over here, it is negative over here. So in that case, if you do not take the squares and do not take the absolute measures, and if you simply sum them, your total sum will be zero. So you would say that, you would conclude that your model is doing a very good job, where in actual scenario it is not. Yeah, that's why we take a modulus, absolute values, and that's why we take a square of that. Okay, so that is about how can you measure the performance of a regression model. These are a few assumptions in a regression model that we have, that there should be a linear relationship, there should not be multi-collinearity present, residuals should have a constant variance, that is called heteroscedasticity, and residuals must be normally distributed. So in the interest of time, I would not spend a lot of time on the assumptions. I would request all of you to explore more on the assumption side, right? And but these slides, these codes are checked in onto the GitHub repository, so please feel free to explore them. Yeah, I'll move to the next algorithm, which is decision tree. Now, decision trees are one of the most simple models, very simple models to understand. It is as simple, if it is a simple block of if else statement, if else, if else, if else. Now, what it means is that, let's say if you want to predict that whether the customer, sorry, what is my demand going to be? So, you will start with your root node, your first node, right? And then you would define a decision, that if the last year demand was above 100, yes, no. Okay, so the way it goes is like this. I'll just create that for you. So over here, demand less than 100. Okay, here yes, here it is no, right? So again, if it is no, then again more nodes will come, more nodes will come, more nodes will come, like an if-else block. Okay, and that process, it will continue. Okay, ultimately you would reach a, a decision over there, right? Or you would find a value. Okay, now in decision tree, you would want to, decision trees again, they can be used for both classification and regression problems. We would study the classification problems in the next session, but in today's session, since we are talking about regression problems, so you can measure the the impurity in a decision tree using variance. What is impurity? Ultimately what decision tree is trying to do is, it is trying to segregate the the data points which are in the same category. Okay, that means if they follow a certain rule, they will be in the same category. So, or if you started your data points over here, your demand was less than 100, okay, no, then let's say again you again made a rule over here that was it let's say was the store in a metro. Okay, so it is yes over here and no over here. So if the store was in a metro, okay, was it, is it selling, how many competition stores are near to that? Let's say less than 5 or more than 5. So more than 5 over here, right? It is a second, the next node over there. That's how the decision tree would create its decision based on if else block. So with impurity, we want to create the nodes, these decision nodes, these nodes. Once we are splitting them, we want to create, we want them to be as pure as possible. What it means? That means they should be very different from each other, right? We should try to make them as different from each other as possible, and they should have observations which belong to the same category as much as possible. So let's say if I'm doing a splitting based on gender, right? This is male, this is female. So I would try to keep all the female population in this one as much as possible. Okay. So in decision tree, that's what you want to achieve. So decision tree, what happens is you have a root node, you split it, and then you reach your decision node. Then if you are no longer to split it, you reach a terminal node. Okay. In a decision tree, you can have a branch also, which is a separate decision tree in itself, right? And ultimately, everything will come down to the root node or the first node. Now, this is one way, where you are splitting it. There can be other decision trees where you are going the top of approach. Okay, so instead of splitting, you are trying to combine. Okay, but mostly you would find that splitting is the way that we follow in the decision tree. And we will talk about the other impurity measures in the next session on classification. But if this is the basic concept about decision tree. So for regression problems, you can measure your impurity using variance, right? And the formula for that is very simple. You simply want to understand, the variance, which is x minus mu. Mu is nothing but your mean, okay? And it is the most common measurement of your dispersion. Again, dispersion means that how varied your data set is. Now, decision trees, they are prone to overfitting. What is overfitting? Overfitting means that your model is able to behave or able to predict very well for your training data set, but not that well for your unseen or testing data set. Let's take a step back from there. I'll just refresh that we discussed last week, the training and testing concept. So if you have a data set, right, you would divide that into 80% trained, let's say, right? You would have 20% as testing, Okay, so training and testing, you would keep your model in like this, so 80% data your model will be training upon historical data, and 20% data set you would keep it for testing purposes. If your model is behaving very well on training data set but not that good on the testing data set, it means that your model is overfitting. You do not want your models to overfit, because if your models are overfitting, that means your model will not perform very well in the real world, right? Ultimately, you would want your models to perform very well on the unseen data sets, on the new incoming unseen data sets. But if your models are overfitting, then you cannot do that. That is no, your model is no use for you. Decision trees are prone to overfit, right? And one of the best ways to tackle overfit is pruning. We'll see that in the code in a bit, right? But pruning is one of the ways to tackle overfitting in decision trees. Okay, we will see the code. Don't worry on that. Yeah. The next set of algorithms are ensemble-based models. The bagging and boosting algorithms. What are they? Bagging and boosting algorithm. So if you look at your algorithm that we have discussed so far, decision trees or linear regression, all of that, right? They are standalone models, single models. Ensemble learning, it is a combination of multiple algorithms, and the most famous bagging algorithm is a is a random forest, right? Um, so what happens in random forest is, in random forest you take subsets of data. Okay, you take subsets of data with repetition. So let's say if you have 100,000 data sets, you would take subsets of that with repetition, and you would create multiple decision trees on that. That's why forest, right? You would create multiple decision trees on that. And once you have created your decision trees, you would make the final decision based on an average. Okay, since we are discussing regression, it is an average. If it is a classification problem, it will be a vote. Okay, so if it is a classification problem where you simply want to predict yes, no, or good, bad, so whatever the individual decision trees they predict, you would take a vote of that. That is a classification problem. In regression problems, you would take an average of all the predicted values, right? And that is your values of your regression problems, right? That will be the final values of your regression problem. Okay, so now the random forest and the decision trees, they are very useful because they allow you to uh, to combine the power of multiple separate algorithms. Okay, boosting, what is boosting? Boosting algorithms, they are again ensemble learning models. The most famous ones are gradient boosting and extreme gradient boostings. What they do, they iteratively build on the previous model. Like in the first iteration, you build a model, you got some errors over there, you got some challenges, or some errors with your model. Your boosting algorithms will look at the errors in the previous model and will try to focus on them, will try to improve them, and iteratively will try to improve your model till the point you reach an end state, or maybe the most optimized state. That is they are called your boosting algorithms. Okay, now a small tip over here. Many times your question would be that which algorithm should I select, which algorithm should I not select. If you do not know anything, if you have, let's say, very less time, and you want to have an algorithm, you want to create a model, you can start with random forest. That's what, from my humble experience, I can suggest that random forest is one of the most versatile algorithm, I would say. Less prone to overfitting, and easier to build also. Yeah. So you can start with random forest. If you do not have any way, if you do not know where to start, or which model should I start with. But that being said, that being said, all of these models, all of these algorithms, they are used in the industry to to build our models. Now let's move to the code part. I'll we will discuss about uh, the code over here. Okay. Um, so the first algorithm is my linear regression model, right? So over here, I have imported all my libraries, pandas, numpy, matplotlib, my visualization libraries, and over here I'm importing my dataset, my housing dataset. So it is a very simple linear regression. I have my price. I'll just zoom it a bit. Yeah, I have my price. I have my square feet of the house. Price is my target variable. Okay, and I want to study. I want to explain a lot of things. All the steps. But I will talk about the important steps over here. Again, the code, the datasets are checked in onto the GitHub repository. Please feel free to take it from there. Right. So over here we are finding out are there any null values over there. Okay, then we have removed one of the columns over here, unnamed, which is not required. So this is my final data set, my square feet and my price. Okay, I want to build a regression model for this problem. So over here I am splitting into training and testing. From scikit-learn library, I have my train test module, and I am splitting into train test 80%, 20%. That is the split over here. A random state 0, what it means is that if you want to recreate the same split again, okay, if you want to recreate the same split, if you want to repeat the experiment, the numbers, you can go for random state. Again, random state, you can give any numerical value over here. So if you give random state equal to 10, and if you give random state 10 again, next time you will get the same numbers. So this is my simple linear regression model, right? This is my regression. I just invoked linear regression for my scikit-learn library, linear regression, fit x-train, y-train, and I want to predict, right? So again, this is my training set, this is my testing set, and I'm predicting on this is my training set over here, this is my testing set over here. So you can see that all these red dots, they are the data points that we have. My blue line is the line of best fit. Okay, this is the line of best fit based on my simple linear regression model. Okay, so if I want to calculate the mean squared error out of that, so this is my, again, from scikit-learn. The scikit-learn library is one of that library which is omnipresent. You will be using scikit-learn for most of your purposes, for creation of the models, for measuring the performance of the models, all of that. Okay, so from scikit-learn I imported my mean squared error. From scikit-learn I imported my r square, right? And I'm simply calculating my mean squared error over here between my y test and my y predicted. So between my actual values and my predicted values, I'm calculating my mean squared error. Similarly, I'm calculating my r square between the two, right? That is my simple linear regression. My multiple linear regression, if I extend this problem to my multiple linear regression, I would have more than one variables. I would have a square feet, the views that have bedrooms, bathrooms, square feet of the basement, and finally the price, right? So again, the same data sets, I would want to have over here. I do have an additional variable, that is my bedrooms or number of bedrooms, right? So if I want to, that is, I want to take that variable as is. Similarly, I have my categorical variable as a view, which is yes, no. So I want to create that into multiple variables, right? Into a categorical variable using one-hot encoding. That is the process for that. Get dummies. Okay, one-hot encoding, what it does is, so let's say if you have if you have a variable gender, right, as male and female, you cannot pass gender as a variable to your model, and that is why you use one-hot encoding. What it does is, so let's say if your data set is let's say ID and gender, and let's say revenue, right, and ID 1, 2, 3, 4, gender male, female, male, female, revenue 100, 111, 102, 103, right? So if you convert this gender variable to one-hot encoding, what it'll do is it'll do something like this: male, female, male is 1, female is 0, male is female, for this one, for this observation, it is 0, it is 1, right? It is 1 and 0 for this one, it is 0 and 1 for this one. So this is how one-hot encoding will convert your categorical variable to your numeric variable. Yeah. So this is what we are doing over here in this example also. Okay. But long story short, again, I again split my data into training and testing, and over here again I invoked my linear regression model. Okay. Now let's spend some time over here. So I'm splitting into training and testing. Okay, so train test split is there, 80-20 split, 70-30 split, whatever you want to do. Then I'm fitting my model over here. What is happening in the background in this line? So linear regression model or library or the algorithm was invoked, and this multiple linear regression, it is fitting the X train and Y train. So X train, it contains all of my independent variables, and Y train contains my dependent variable, in this case price, right? And this model is getting fitted over here, right? Based on that fitted model, I am predicting over here, right? So I'm getting my Y prediction based on the model which has been fitted. I am predicting over here, predicting the values. Sorry, predicting the values for what? X test, the unseen testing data, unseen independent variables. So I'm getting my values for them. And again, for them, I'm calculating my mean squared error, I'm calculating my R square. So yeah, if you look at your model, right, your R square value is coming to be 53%. Now 53% is not a very good model. 53% R square is not a very healthy model, right? Ideally, you would want your R square to be more than 75%. Generally, generally you would want it to be more than 75% or more than 80%, right? R square, adjusted R square, just have a look over here. Adjusted R square is slightly less than the R square. So like the concept we discussed on the adjusted R square, right? It penalizes your model more. Okay. So I would want my, again, adjusted R square is again 53%, not a very healthy model over here, right? So let's say if I have one more data set over here, right? House data set. Again, I can look at my data set like this. And over here, this one over here, this is the correlation plot between all the variables that I have. Remember, we discussed about the assumptions of linear regression. So there should not be multi-collinearity present in your model, right? So using the correlation plot, you can test the multi-collinearity between your different variables. Like you can see over here, some variables, like they have a collinearity of 0.75. 0.75 is a high collinearity. 0.88 is again a very collinear, very correlated variables over here, which have a correlation of 0.88. So you would want to treat such variables over here. I'm not talking about my my data cleaning, again, in the interest of time, because we have to discuss the random forest and decision trees. But that being said, you please feel free to explore this code. Again, this code is checked into the GitHub repository, and use it to complete your data cleaning your feature selection, all of that, right? Very simple code to understand, and the comments are also there, right? Now I would move to the next set of algorithms, which are decision trees and random forest. Now over here, my data set, it has these independent variables: acidity, chlorides and sulfur dioxide, pH, sulfates, and I want to predict the quality of my wine. So all these data sets, they are available from Kaggle. Okay, so I want to predict my output variable, between a score between 0 and 10 for my target variable. So again, I imported my decision tree classifier, and there are again many libraries. Scikit-learn, you can see that again, scikit-learn library has been used for my decision trees, right? And I did my descriptive stats, I did my univariate. Now I wanted to explore on this one because this is how you can do EDA of your data. So if your wine quality is your variable, right? So this is the quality of your wine, right? Now this example over here for the decision trees and random forest one, this is a classification problem I'm showing to you. I know that we will be discussing classification problems in the next session, but I wanted to show to you the EDA that you can do for your models, right? For your data sets. Okay, and again, you can plot your models like this. You can plot your variables in a histogram shape by what it shows that your variable fixed acidity is mostly normally distributed. There is a left skew over here, a slight skew, but you can think it as a mostly normally distributed variable over here, right? Again, you can create your correlation plots to measure the relationship between your different variables. Okay, now what correlation tells you now? Okay, what correlation tells you is that what is the relationship between these variables. That means if number of invoices and number of customers. So obviously you would imagine that there will be a relationship between the number of customers and number of invoices. Higher the number of customers, higher the number of invoices. What it means that in real world you might want to uh, delete one of the variables from your final model. You might not select both the variables in your final model. Okay, again, it is this variable selection in your final model. It will be dependent on the significance of that particular variable. Now that's I want to discuss right now, that how do you select the significant variables, right? Your variables which are significant, mostly you can find out the p-values of them, right? p-values p-value, it means that how significant your variable is in making a prediction. As a rule of thumb, if your p-value is less than 0.05, that means your variable is a significant variable. Okay, what it means that it is less than 5% chance that your independent variable is impacting the dependent variable by chance. Okay, so in simple terms, it means that it is less than 5% chance, right? It is less than 5% probable that your dependent and independent variables are not related, or in other words, your dependent and independent variables, they have a relationship between them. Okay, so this is how you can select your significant variables. Again, p-values, they are an output which are given by your model, and in the code you would find that we do have we do have codes, where we explore our models. We get the p-values for each of the variables, and based on that you can shortlist which variables you want to have. Okay, now coming back to the code, I'll study this code. We will study this code next time again, in the next class, because it is a supervised learning, sorry, classification problem. But I wanted to show you that uh, creation of the model is very simple. This is your random forest. This is your ADA boost. Okay, your boosting. Okay, we'll explore this code in much detail in the next session. But I want to emphasize on one part, that creation of your model is very easy. Interpretation of the results is the challenging part. Selection of the model is the challenging part. Now, how would you select? Let's say if you created multiple algorithms, right? And how would you select your best model? So what would happen in the case of regression problems, right? In the case of regression problems, what you can do is, let's say you created a multiple linear regression problem. You created the second iteration of that. You created a decision tree iteration 1. You created a random forest iteration 1, decision tree iteration 2, random forest iteration 2. These are the models which you create. So you can select on the adjusted R square, right? That is one of the good ways. And you can you can select your RMC and your mean absolute error, right? So if you work on these parameters, you would be able to get, you will be able to fit your this table. Okay, this is the first thing that you would do, right? The next thing you would do is this you would do on the training set, right? The same thing you would repeat on your testing set. The same thing you would repeat on your out of time data set. What is out of time data set? So let's say you built your model using 2015 to 2018 data set, right? Okay, then you choose 2019 as out of time. That means this data set of 2019 is not a part of your original data set. You will use your 2019 as completely blind, completely unseen data set, right? And then you would measure the performance of a model over there. If your model is performing very well on 2019, then you would say that, yes, my model is a robust model. My model is a good model. Okay. So based on these KPIs, these three primary KPIs, you can select between all the you can pick and choose which model you would want to choose in your final production environment. These three KPIs. Yeah. Um, if there is a if they are similar, if they are mostly comparable, then go for the simpler model, right? So let's say if your decision tree and random forest both are giving you similar results, go for decision tree. Why? Because decision tree is simpler model to explain, simpler model to understand and maintain as compared to a random forest model, right?